Welcome to the Robotics Institute seminar. Today our guest is Jonathan Hurst from Oregon State. I first met Jonathan when he was a freshman. He came wandering into my office, you know, a young guy. And at the time I was writing a DARPA proposal on legged locomotion, if you can imagine that. And we shared some ideas and so forth. He asked if he could hang around the lab and basically be a lab rat. And I said, yeah, sure, fine. So we did that and took courses in mechanical engineering. He was a BS from CMU in mechanical engineering. He was president at one point of the robotics club here. I think at that time they built a walking machine called a frame walker, which won the big prize in the exhibition in Colorado, which was great. Went on for his master's and PhDs, and he always was interested in making robots that could not only walk but to run, which is another step above walking, of course. So I think it's time to welcome back to CMU, Oregon State University College of Engineering Dean's Professor Jonathan Hurst.
Thank you, Ralph. This is really great. I spent an awful lot of Fridays sitting where you are, seeing all the people from the robotics community coming through the Robotics Institute and giving talks. I sure have valued the education I got here and been building something smaller but growing in Oregon State along a similar mold. So I'll tell you a little bit about it. So yes, I'm at Oregon State University. I'm also now CTO of Agility Robotics, where we're doing some transferring this technology into a commercial product. This talk is primarily going to be about how we try to understand things from animals and not copy them. We're just trying to first understand exactly what's going on, exactly why it's happening, and represent that in some symbolic form, some math model, something where you can recreate the dynamics. And then, based on an understanding of exactly what's going on with this reduced order model or with simplified models that we think might capture the physics of what we see in animals that we want to be able to reproduce, implement it on a machine. And this machine, of course, doesn't look physically or morphologically anything like an animal, because that's not what we're trying to reproduce. We're trying to reproduce the behaviors or the capabilities. And our approach to reproducing the capabilities is to reproduce the dynamics. And we're building it out of electric motors and carbon fiber and things like that instead of muscles and bones. So I'll repeat that idea a bunch of times throughout the talk. I'll start with a little bit of background about myself, I think. Maybe. There's the frame walker that Ralph mentioned. That picture was taken right outside of FRC. And a little servo-driven robot that primarily taught me that robots are hard. I mean, it did not work.
The frame walker is still in the robot farm.
Oh yeah, I think they mounted that up on the wall.
Right above the 100-year-old lathe.
Nice. It's not 100 years yet, but that was fun. That was a lot of my life spent down in the basement of the Field Robotics Center building this thing for a couple of years. In Ralph's lab, I worked on this, the actuator with mechanically adjustable series compliance. The idea is that this is a joint, a knee joint out there, and like a thigh. This would be the hip joint. Prototype leg, where you can change the co-contraction of these antagonistic springs and change the physical stiffness out at the end. Until I learned that there's no reason to do that for walking and running. But still, learned a lot. I also worked on the Rex robot. This is, I just saw this one in Ralph's lab, but that picture is 10 years old or more. And that was great. And I built Mabel and Thumper. This was working with Jesse Grizzle at the University of Michigan. The deal was I build and deliver a robot to him so that he can do controls, and he buys enough spare parts that somehow ended up in my lab that I get to have a monopod and hop that around and finish my PhD work and my thesis work with that. So then I spent a lot of time down here in A level in the corner. Now I'm at Oregon State, and when I got there really wasn't much in the way of robotics, but it's been a very fertile ground. A lot of people have really been encouraging and supportive, and we've been hiring and building. This is our new facility. It's about the size of FRC. My lab is this section down here. That's my big treadmill I have for robots to run on it. We started last year with a new graduate program. So you can get MS and PhD in robotics now at Oregon State. And we're going to be soon the new Center for Autonomy, Intelligence, Robotics and Intelligence Systems. So if you're interested or curious about any of this stuff, just look at the website. We've got about 8 faculty. So we're growing. We don't have, what do you have, 100? It's not a competition. It's not a competition. Okay, so starting on the technical side of things, I start with asking the question, what is walking and what is running? If you crack open a dictionary and you look at the dictionary definition, it says that if you walk or move at a regular and slow pace by lifting and setting down one foot one after the other, where you usually have at least one foot on the ground at a time, that's walking. But if you want to even define the word foot for a robot, that's not so easy. Is an egg that's rolling down a hill. It's maybe matches the definition of running. It's moving at a fast speed, faster than a walk, where it's got an aerial phase where all the feet are off the ground at a time. But I think most people would agree that's not really running. So the reason I bring that up is because our goal is not to walk or run. We're not trying to make something that looks like an animal and looks like it's walking and running or is by some definition. We're trying to meet or exceed performance goals. And this is an example of a performance task. This bird, guinea fowl, is running down a runway that it's been down 100 times. A piece of tissue paper has always been over that spot on the ground. And up until this time, there's never been a hole there. It's been able to just run over that spot. So this bird has full confidence that it's just going to run down the runway, being motivated by that broom that's chasing it. You know. This time, though, its foot just happens to break through. And you see it really doesn't disturb the gait hardly at all. I think that's amazing. That's a 40% of the leg length is the level of the disturbance, that unexpected pothole on the ground. And these birds run on birdseed. They're incredibly efficient. And they are very robust. I mean, they're versatile. They can go lots and lots of places. That's what we want. We want those achievements. Now, I think, and the way that we approach this is looking at how exactly is it able to achieve that, try to hypothesize based on collaborators, like collaborating with Monica Daly and other people in the community, to try and get out these key hints and principles about what are they doing. And fundamental principles like this should apply equally to animals or robots. So if you think you understand it in an animal, you should be able to reproduce it in a robot. I don't see why not. Again, principles and morphology are not the same thing. I really think a lot of people, because walking is so familiar and you see it everywhere, and say a baby giraffe is just born and gets up and walks, people think it's easier than it is. But there's so many millions of years of the evolution behind this. It's built in. It's built into neurons. It's built into the physical hardware. So how do you design and build something from scratch to do this? We just don't understand how to do it. I really think if we understood it, we'd be able to do it. I mean, motors are more than strong enough. Materials are light enough. And computers are fast enough. So those really, it's not technology, it's not the engineering that's the impediment. It's knowing how to implement, how to do it right. We clearly don't understand it. You've all seen this, so I won't linger. But I'm sorry. They don't show that robot actually getting back up. I mean, this is still a great achievement. If you're a roboticist, you look at the whole thing and it's pretty impressive. But to the outside world, this is disappointing after watching movies. If we really understood how to do this, It wouldn't look like this. Okay, so skip the rest of those. If we really understand it and we can make robots that can go anywhere people can go and with the same efficiency and versatility, I think the impact is really going to be huge. We're going to see this in every aspect of life. Now, of course, prosthetic limbs, making people close to able-bodied again, or even better than able-bodied if the robot has a little bit more power, so long as it's actually behaving like the biological limb and is able to coordinate with your body well. A lot of that is all about the dynamics and understanding the physics of how it works. Or exoskeletons. I imagine, I hope, I believe actually, that wheelchairs are going to be an anachronism someday. And you'll be able to put on fairly unobtrusive, lightweight exoskeletons and get around. But we're going to have to understand how to do that, how to not treat the person inside like a puppet, and instead be able to work with the biology right there. But I think the biggest and the most important application that's going to affect the most lives, that's going to be as, I don't know, everybody's got a smartphone, it's going to be that kind of thing, is having the robots that can go in buildings and outside and just go anywhere. The mobility, solve the mobility problem of machines. If you watch the first half of the movie I, Robot, it's really a utopia. It's really a great story. You just have to stop when all the lights turn red and don't watch the rest of it. An example might be just, if you don't know if somebody's in the burning building as a fire chief, are you going to send your firefighters in to save that maybe person or not? Tough choice, but if it's a robot, just go for it. There's all kinds of situations like that. So our approach to trying to achieve this goal of having machines go everywhere that a person can go is to try and, again, understand what's going on with animals, understand these principles, and then demonstrate it and demonstrate that understanding on a machine. It's really a virtuous cycle. You kind of learn an awful lot by trying something that you thought was going to work and seeing exactly how it doesn't and making slight changes and then watching how it improves or makes it harder. And I worded this specifically, the dynamical phenomenon of legged locomotion. I think of legged locomotion the way you might think of how a mechanical clock works or how a grandfather clock. That has inherent stability for timekeeping based on a pendulum or a spring and a mass. And that's something that exists whether you understand it or know about it or create it or not. If we wiped out all knowledge of how a grandfather clock works, people would very quickly discover it and find that a pendulum keeps time and things like that. I think legged locomotion is exactly like that, but it involves springs and masses and a lot more complexity than something like a grandfather clock. I don't think that you can explore this very well in simulations. I think that a lot of times simulations, I've seen many simulations of successful machines walking and running around, and if you dig down enough, you find some simplifying assumption that isn't feasible or realistic and it's not possible to do. Doing it on a machine sends you in the right, forces you to go in certain directions. So I think we're just beginning to really understand this integration of passive dynamics and applied control and how it applies to legged locomotion in particular. Now I know a lot of you in this room, this is probably old news. A lot of you I know I've seen at conferences and things like that, so you've probably seen me say this many, many times. But just to be clear for everybody in the room, the passive dynamics are any behavior when the power is off. If a person is unconscious or the power is off, however your machine operates, the inertia of your rotors, okay, any stiffness in the system, any friction in the bearings, any backlash, that's all passive dynamics. That passive dynamics can either help your task and contribute to achieving what you're trying to achieve, or it can be an impediment and really get in the way. And so when you design a robot without thinking about your dynamic behavior controls, you design it with kinematics first, then you say, now I will build a model of my robot and try and control it. The odds are that those passive dynamics are going to be an impediment and are going to get in your way and are going to be a problem that you have to try and control around. Applied control is, of course, the little additions that you give. So that's my daughter Jane. And on a swing, you learn to pump the swing. That means you have to give it just a little kick each time. It's not a lot, but you're relying mostly on the dynamics of the pendulum in order to create the particular motion that you want. You're not intentionally creating this trajectory or doing a path planning for a specific trajectory. So I think similarly, it's kind of crazy to try and do trajectory following for a walking robot. It's just not like that. It's a dynamical phenomenon. Another one of my favorite. Yeah. Oh,
Can I ask you a
Sid.
question?
Okay.
You made, thank you. So you mentioned that you don't have to do trajectory following, or,
Yeah.
But obviously when you're swinging freely, it's more of a natural phenomenon. But if you're walking on steps, or if your daughter is,
Yeah.
Jumping over things to
Yeah.
get to a dastardly destination,
Uh-huh.
doesn't she have to do some planning?
Sure. No, planning is, yeah, but I think it's more like Mike was showing me in Ralph's lab at the BallBot, where you think about planning through your dynamic state space. So you have to know what the dynamics are of your machine, and you kind of want to create the dynamics of your machine to help do what you're doing. So she has some trajectory here, which is probably phase locked in some way to the passive dynamics, and pick a time to trigger when you choose a trajectory for the pumping of the leg. So there's always planning, choosing when you're going to do that, and there's probably trajectories, but it's not the high-level trajectory of I want my swing to do this thing, and then force it to do that, even though by applying torques to the bar that may or may not fight with the passive dynamics of the pendulum. So what I'm trying to suggest here is that all of these dynamical systems are going to be an integration. They're going to be a partnership between the passive dynamics and the controls. And it's very important to think carefully about what passive dynamics do you want for the task you're trying to achieve. Does that answer the question? Great. Okay. So I think I've got a couple of videos here that I think really illustrate that combination. I think this guy is obviously aiming a little bit. You can't miss. You have to catch. But it's a pendulum. And notice a couple steps at the top right there. It swings from brachiation to walking. It shows, I think, a lot of similarity in the springs and the pendulum between those motions. They're very, very similar. This fish is 100% passive dynamics because it's swimming upstream. There's a little rock right there. It's actually dead. It's a dead fish that's swimming upstream. And if it had controls, it would know to just kind of nudge itself and kind of nudge those passive dynamics to keep that under control and keep that going in the right way. But it's dead. So specifically for legged locomotion, these are the passive dynamics that I would like to tell you as fact, but I expect a few people would argue with me in this room. These are the passive dynamics that I believe are the foundation of legged locomotion, this spring mass behavior. Now, this theory showing that the bipedal spring mass model can reproduce the characteristic ground reaction forces for walking and running, that was Hartmut Geyer here, who 2006, that's not that long ago, is the very first time anybody ever said that. That's amazing to me. This is a theoretical result that even though people have been thinking about walking and running for centuries, probably, millennia, I don't know, this I think really kind of cracked open an idea that's important. Now, we looked at ostrich, turkeys, guinea fowl, pheasants, and quail. This is with Monica Daly. And look, this was hundreds of experiments, hundreds of runs of data. And my student Christian Hubicki put together this very simple reduced order model with the idea that birds don't actually look like this, or animals in general, don't actually have this perfectly symmetrical spring mass gait. There's always this little tail going right there. So what's our theory for that? And a little bit of damping. Everything's going to have a little bit of damping. He put together a really simple model with a little bit of damping and an optimal work actuation in series with that damping, and showed a very good match to this data for this huge range of birds. It doesn't prove anything. It just says, here's a model that can reproduce the set of data that we took. But it's our best guess that we're actually this is capturing the real physics of what's going on in the system. So that's what we wanted to show with the robot. Is this just a model that maybe reproduces some behavior, or is it actually capturing the physics and the fundamental principles behind it? So we start with a simple model, get a little bit more complicated, a little bit more like a robot, and we end up with our prototype robot leg. So here I'm going to make an argument. This is straight out of my thesis. So I've made this argument for years and years. But it's important to keep on repeating, I think. The question is, do you want to create this spring mass behavior, which we've just described? Maybe I've convinced you that this is an important foundation for legged locomotion. If you had really great actuators, you could do it like this. You can just control in software that behavior, and you can get all of the behaviors that you want. And maybe the spring mass is the way to do it, maybe something else is the way to do it. Or you can build it in hardware, in which case you're absolutely stuck with that passive dynamics behavior. And if that passive dynamic behavior kind of gets in your way, tough is just going to limit your abilities. So there's definite trade-offs between doing it this way. And I just want to tell you why we do it this way, why we put the spring in the hardware and implement the passive dynamics through the physical system. Basically, it's about the collisions with the ground, energy efficiency in the system, and power capacity. So starting with the inelastic collisions. If you ignore any sort of mechanical springs, and you think about this simple system coming towards the ground with this velocity, here's your motor and a gear right there, and it's not spinning at all. So at the instant before impact, it's stationary. The instant after impact, it has some rotational velocity. That's an inelastic collision. And that equation right there describes the energy loss to that inelastic collision. If on, say, something like Osimo, you have a little motor and 100 to 1 or 150 to 1 gear ratio, the reflected inertia here, the effective inertia that you're going to feel from this, is about on the same order as the mass of the robot. And so you lose more than 50% of your energy at that instant of collision. That's ignoring the fact that you're going to have a very, very large force spike right there that is likely to break a lot of things. So when Osimo tries to run, it's very hard on the robot, just for those inelastic collisions. It takes a lot of power, too, to get you off the ground. I guess I'll get to that. Energy efficiency. If you're trying to do regeneration, now remember, after your collision losses, you still have maybe 40% of your gait energy. And that's in the velocity of that motor spinning now. And you want to reduce that speed and then accelerate your robot back. So you want to take that energy, store it, and give it back. If you need to go through your gearbox, your motor, your amplifier, and chemistry and your battery, and then push it all the way back out, your efficiency, maybe if you're Songbei Kim, is pretty good because he was very, very careful about all this stuff on the Cheetah robot. For most people, that's in the 10% range. It's very hard to get that efficiency to be anywhere decent. On a spring, if you're Ben Brown, then you get better than 90%. And then the power capacity is really a compelling argument. When you lift off the ground and you're bouncing, that's at high force and it's at high speed. It's a very high power motion. For a tiny little spring, you only need about 80 grams to do something like 75 joules, and that's, I don't remember, I chose something like a 60 kilogram robot hopping a certain amount height, just so I could do the comparison between them. And a motor, just this, without the housing and no bearings and nothing, is about 2.2 kilograms to get the same power output. It doesn't make sense to try and generate your power output with an electric motor. It just makes a lot more sense to use springs to do what springs are good at, like the high power. Use motors to do what motors are good at, which is the continuous kind of power output. And hopefully you've all seen this before. Garth Zegelin and Ben Brown's robot from a while back. But this and the Aero Monopod 2, and those are kind of my background. I don't really buy in much into the humanoid robots. So I've already said this is our approach. Others have taken this approach. Passive springs in there and a very small motor to kind of keep that passive dynamic behavior going. Back to Mark Rabert doing this stuff with, yes, air springs and hydraulics, but look at what that, no robot's ever done that since. It did a flip. Now when was this? 1994? And they had robots running 10, 15. Why isn't everybody copying this? I don't understand. People still build humanoids that do this kind of walk, and I don't understand. So this is our machine, ATRIAS. The whole concept behind ATRIAS, okay? The whole concept behind ATRIAS is that we have a simple math model. That's the model that we think we understand. That's the model we think is capturing the physics of what animals do. It's the model we think we can control. Let's build a robot that is as close as physically possible to that model and be about human scale and be out in the world. And that's where ATRIAS comes from. Assume the robot is a sphere. And the idea is we really can just assume the robot is this simple dynamic model, apply the controller to the simple dynamic model, and it's going to work on the robot. That's the idea. I guess this is just telling me, yeah, what did I just say? Define the behavior that you want, and then design the passive dynamics to work with your controller to integrate that behavior. So it's very much an integrated system. In the beginning, when I first got to Oregon State, this was a cable drive. The motor is here in the center, large pulleys here, and then these are a step down, and they spin around the motor housing. So this is like a planetary gear that'll spin around it. But it's all cable drives, no gears anywhere on the robot. And we built a prototype, and we did have this hopping around the room. Now the problem with this machine is it was this whole dinner plate sized pulley sweeps all the way around here and all the way back. It's very difficult with the robot if you want to do adduction, abduction, not even turning, not even yaw. There's this huge keep out space where these dinner plate things are spinning around. We can't figure out where to put a body on this thing. There's just too much space. It was too big. It was a problem to do cable drives. We could not figure out how to get cable drives into a form that would work. So we reverted to these harmonic drives that we put in there, which are terrible. I hate harmonic drives. 60% efficient or something like that in our application because they're small, very high torque capacity and so on. But they did work. They did get the job done. So we have these big motors in there from Ematech right in the core, and then this 4-bar linkage for the leg so that the leg can extend and retract like this and swing back and forth like so. And these big plate springs, fiberglass plate springs for containing the energy of the running gait. Started building. There were a lot of parts, a lot of machinists, and made 3 of them. So one of them, I know a lot of you have seen it in Hartmut's lab. One of them's at the University of Michigan, and we have ours still at Oregon State. We traveled a little bit with it. We did take it out to the Royal Veterinary College and do a photo shoot. This is the runway. Had the robot run, and I think this was the first time the robot walked outside. Now the reason we had the robot walking outside, this is very, very early in the project, is because they couldn't, for some rules or reasons, get the rope attachment to the ceiling for the boom. So they took it outside and wrapped a rope around a tree branch and then just walked around out there. It worked. Worked. Okay, now I get to the actual technical content of the talk. I've given you the background, I've given you the foundation of what it is that we're trying to do, the approach we're trying to do. And I want to tell you how we control this thing. It's a lot more based on understanding the physics and having that understanding of how you want to control the physics and the passive dynamics than it is about a closed form controller. Now there's a lot of detail behind this. There's a lot of pretty good control theory and computer science and things that my students do because I don't know how. But I do have good intuition for the dynamics and how these things move. And these are the key pieces that enable the robot to function. So to start with, of course, we made a spring mass model. Okay? Near massless legs, that's why our motors are right here. These are very lightweight carbon fiber. The leg springs, the mass is concentrated all right here. The center mass is right about there. We couldn't quite get it down to the middle just because we needed our computer and batteries and everything. Practically though, we have motors, we have adduction, abduction, which is not part of the model. All of the overhead that you need to keep a robot going. And this is the very first just demonstration where what he's doing is holding the length of the motors constant. So the motors can't change their leg length, or at least the very tight PD control is holding the leg length constant, and it's applying 0 torque at the hip. That's it. Also, it's following kind of a not quite hybrid zero dynamics, but a clock where it matches where you are on the gait and keeps the other foot there. So that's why he has to push it to walk around. So that's all the controller is doing. 0 torque at the hip except for placing the leg and holding the leg length constant. And there's what we get. Just using the spring mass behavior and giving it and pushing it around the room, we get the characteristic spring mass walking gait behavior. That dotted line is what you get from the theory. The solid line is what we get from our robot. And that's what you see for a person walking. Now the first thing that I get a lot is, who cares? So what? You've kind of demonstrated something that looks like a person, but why does that really even matter? Well, why it matters is because what it can do, but I'll get there. Here we are doing the first passive hop. Same kind of idea where we're holding the leg length constant, holding 0 torque at the hip, and just throwing it. And then looking at the ground reaction forces, there's what a person looks like. They have a heel strike. Our robot doesn't have a heel, so we don't have the heel strike, but for the most part, it's pretty close to what this spring mass model does. Okay, so that's just to show step 1, robot is a spring mass system. Okay, step 2, we had to kind of mix time-based control and state-based control. We don't want to, there's a lot of flexibility in the robot. If you try to do closed-loop control of this thing, it's very hard to have enough bandwidth with your actuators, given the fact that they have so much inertia, to be able to take any sort of oscillations out of the springs and things like that. So we don't even worry about it. What it's doing is it's going to just be the stepping side by side, which is a feed-forward clock trajectory. And maybe some people would call that, what's RPG, not RPGs, CPGs. I had lots of names for what, but it's just a time-based controller that's kind of tied to the state-based control. In this case, the state-based control is the velocity. So it places the angle of the leg based on the velocity of the robot. And it just stands there and sets side by side. Now it has no feet, so it has to do that. If you had no feet, you would also have to do that. And you can try this by wearing stilts. So to visualize what it's like to be the robot, wrap yourself in a carpet so that you can't see anything, so you can't use your arms, so you can't really bend your body very much, and wear stilts. And then let somebody randomly kick you every now and then. And if you have all of those caveats, the robot does pretty well. People can do about that well. Hybrid transitions are a real challenge. Have many of you run into this before? Some point at which you're going to have an impact and you need to change your control from one phase until after the impact, a different phase, a different control method. We don't have any sort of toe switches at all right here. We do a very gradual transition. We have the swing phase control and the stance phase control are different. Both controllers are always running, and they each have an influence that is proportional to the amount of force that's being applied on the ground, because we can measure the force that's being applied on the ground. So in the swing, there's very low force, so the swing leg control is really the one that controls the torque on the motors. When you pick your location, both of these controllers, the trajectory that you want to follow is pretty much tangent. It's about the same for a pretty good region out at the start and the end of the stride. So it doesn't matter when you hit the ground. If you hit the ground early or if you hit the ground late, the controller was going to be doing the same input or the same thing anyway. And just based on the physics, the behavior or the response is going to be different because now you're applying forces or you're not, but the controller is not doing anything different. So there is no discrete transition at the hybrid transition from swing phase to stance phase. So it doesn't know that these obstacles are here. We just tell the robot that there's flat ground, walk forward, and then it goes. And you can handle quite a lot of disturbance that way. And this is showing that if you think about the velocity vector and just visualize how that velocity vector changes. When it gets a kick, the velocity vector increases. And then in your mind, think a direct proportional controller between velocity vector and leg angle. That's it. Very, very simple. We're controlling the leg angle based on the velocity vector of the center mass. Now, calculating that velocity vector is less easy. It has to do with measuring the angle of the body and the proprioception of the rest, and filtering out a lot of the vibrations and oscillations and things. And energy regulation. Now, we thought a lot about this, about how do you control your velocity, how do you control your hopping height, how do you control the different features that you might want in a gait. And what is really the one thing you care about is probably the amount of energy in the gait. So you think about this from the spring mass point of view. The spring mass system is energetically conservative. You're just redirecting that energy all the time between the spring, the gravitational height of the center of mass, and the velocity of the robot. And so you want to steer that energy through your system. You don't want to control you can control your hopping height by changing your forward speed. So slow down your speed and your hopping height is up high. You can then transition all of that to forward speed. And I've seen this at the aviary, the National Aviary here. There was a lot of really tame birds, ground running birds, and they like to come out, but when they seem a little bit threatened, like I saw a kid coming up behind me when there was a bird right there, the bird slapped the ground and started hopping which I thought was so strange. And then when the kid moved, one leg angle adjustment and the bird was off in the bushes. So it transitioned it put energy into its gait, all in the vertical hop, then steered that energy into the velocity. So if you really want to change your speed, you want to change all these things, you've got a couple of dials, and one of those dials is changing the amount of energy in the gait. And when do you want to change, and how do you control that energy in the gait? It's very hard to do state control where you're measuring the whole energy of your system through feedback. We just add a certain amount every time, and you always want to add it in the last half of stance, because that's when you're pushing yourself the direction you want to go. That's when you're not absorbing it into your spring, which is not the most efficient way, but putting it directly into the gait, and so on. Also, this matches the data I showed you earlier of the work optimal actuation in series with the damped system, so extending the leg in the second half of stance. That's what this does. It's the only thing we're doing to accelerate from a walking gait gradually to a running gait and down to a controlled stop. It's not complicated, it just all works because of this dynamical phenomenon and how stable it is. All we're doing is dialing how much energy is going into the system. Now, one other thing about how to control that energy is dissipation. We ended up with very light gains in our PD controllers with a fair amount of friction in the transmission and a fair amount of damping, and it worked so much better. Before we realized this, it was serendipity. They put a much stiffer spring than it was supposed to be on there, and had very soft gains because there was some problem with it being unstable, and all of a sudden something clicked and it started working really well, and we realized being able to absorb and toss out unwanted energy inputs from all over the place, that's basically the definition of dealing with a disturbance. And if you're just adding energy with every stride, now yes, it's less efficient, but it's so much more stable. And so that's a direct trade-off. So in this video, again, the robot thinks it's going to walk over flat ground. We've changed the gait just a little bit so it's stepping higher so that it won't just trip and fall. But there's no planning, there's no vision, there's no knowledge of the obstacle. And you can see the foot didn't even catch the edge quite right. It just slips off or catches it a little bit wrong. When it lands, it takes just a step or two to recover because it's absorbing a ton of energy. You see it catch its toe right there on the edge, just kind of a weird, happened to catch it in a funny place. Went up too high, loses that energy quickly within a step or two. It's still got a pretty good bounce on the second bounce, and then same thing. And that's very similar. Now, we haven't actually looked at the data, but it's pretty similar to what you'd see in a bird taking a big disturbance and taking a couple of strides to just kind of bleed out that spare energy and kind of settle back into a gait. So energy dissipation is actually really important. And that is one of the big lessons I learned on this project. So bringing it all together, like I said, when the leg force is low, you say, okay, I'm in my swing leg. So it's a time-based leg extension. It's just following kind of something like a sine wave. It's some trajectory. And there's some angle for the leg that you choose just based on your center of mass. And that's both in the adduction-abduction direction and the fore-aft direction. Just predefined trajectories for the swing. We just have a trajectory that's some spline that we kind of made up. Can probably be better or worse. I'm sure we can work on that a little bit. In the stance controller, just when your force is high, you only apply torque at the hip to keep your torso up. That's the only reason. Generally, you want that torque to be 0. You hold your leg length position. Soft PD gains allow you to have a fair amount of damping in the system, and you can control how much of that damping you want if you do it in software. And there's no energy benefit to putting your damping in the physical hardware, so that's one choice where I don't want that to be passive dynamics. I want that to be in the applied control. And then I extend the leg length set point towards the end of stance to add energy, and I can vary how much I do that depending on how much energy I want. Now this is a pretty important point. At the very beginning, remember I said, ATRIAS, assume the robot is a sphere. We can make the robot to behave like the simple spring mass model, and we can control the spring mass model and it'll do what it does. That failed. We spent at least 2 years working with a number of different controls theorists and people in the community. We tried very, very hard, under the gun with a lot of pressure, to force the robot to behave as close as possible to the spring mass model so that any of our leg trajectories and leg choices that work on the ideal slip model are going to work on the robot. And it just was not stable at all. It could sort of do it if you don't really have any disturbances, but remember it's a very underactuated system. There just are a lot of springs and levers where there aren't motors. So it wasn't really feasible. But fortunately, the spring mass system is generally kind of a stable system. It's a nice system. So we didn't get exactly the trajectory we wanted from like it describes in the reduced order model. We started there, and it just drifted off. And this is fine. I don't care. I mean, I don't care if it's exactly this motion right here. This is clearly capturing the spirit of what we were trying to aim for. So I guess, yes, we have to work with the passive dynamics, but the controllers have to be robust enough that your model can be wrong to a pretty good degree and still capture the physics that you want. So just to kind of summarize the control part of it anyway. I had a graduate student who spent a lot more time than he should have on creating nice videos for us.
I can't believe they let you on their football field.
I know, me neither. I think they don't understand how much robots can tear things up. And we don't really want to teach them, so it was fine. Yeah, athletics thought it would be pretty cool, and it was. It's open license music even. No copyright infringement.
So Jonathan, while this is playing, if we were to go into the future 5, 10 years from now, what will this video look like? What's the cool acrobat you're going to show?
Let me answer that question later. I'll answer it though.
In public or private?
Right here, in like 2 minutes. So this is our achievement. This is the thing, this is why we built ATRIAS, to show that we can actually implement the physics and that the model reproduces the physics that and the principles that we're trying to achieve. It's not just a superficial mimic of a symptom, a separate physics that's reproducing the same symptom. It really is capturing the physics we're trying to achieve. ATRIAS is the first robot to ever do this for a walking gait. And the thing that's really cool too is that this was not, we didn't control the ground reaction forces to do this. We had a few months to make the robot work when things started to come into place, and we were aiming for the DARPA Robotics Challenge. We were walking, we hit all those obstacles. We came back and said, hey, let's see what the ground reaction forces look like. And they're doing that. So I think it's a direct link. I don't know, correlation anyway, that having something that's really capable is going to look like that.
I was going to ask this question later, but I feel compelled to ask it now. So you made a very interesting point that like you built a robot,
Yeah.
this magical thing, and then you said, oh, what will the ground reaction forces look like? And it somehow seemed to match humans.
Yes.
Does it mean that you are fantastic at building walking robots, or does it mean that there's a lot of play in the design space of walking robots that even if you made ATRIAS different, it would still produce a profile that looks like
There's a lot of play. You can design any number of different machines. If they generally have this spring mass behavior, that's the key, having the passive dynamics be about right. And then some of these controls ideas that I talked about, you'll get this. And the other thing that's cool about it is you don't have to think very carefully about how you're going to do the transition to a running gait. You just add a little more energy, and this ground reaction force flattens out and then turns into a single peak over several strides. It does it. It's kind of I don't know, it's evidence that we're on the right track. That's why I think this is important. Yeah?
Do you have numbers for the all-up system comparing cost of transport between ATRIAS and sine waves Cheetah? I called them out earlier.
Yeah, not right off the top of my head. So ATRIAS takes something in the vicinity of 400 watts. It's 160 pounds. Cost of transport is in the vicinity of 1. Sung-Bae Kim's reported numbers, I can't remember. I want to say we did a little bit better, but we measured our cost of transport based on electrons coming out of the battery to power everything in the machine. And I think Songbei measured it based on the current that was going to his motors from the amplifier, and not including some of the overhead of the computer and things like that. I'm not exactly sure. He has a really nice system. It's pretty efficient. This has a slightly different approach using the passive dynamics. Also really efficient. Does that answer your question well enough? It is a lot better than any hydraulic machine, just fundamentally. And there's really nothing you're going to be able to do about hydraulics to make it comparable to this. So that's why this is important. It's not that this in itself is a meaningful goal in and of itself. It's just evidence that maybe this is on the right track. So coming up next, ATRIAS is retired, and we're building a new robot. This was a render from about a week ago. It's our first time we've got all the pieces together in one assembly. We aim to finish this robot and have it moving and walking around by the end of this summer. The features that are added, if any of you are curious, this leg configuration is very deliberate. It is absolutely not intended to look like a bird. It's just that's what happens when you have the problem of antagonistic work on ATRIAS, then have your graduate student do a bunch of math for a year, and then calculate configurations that for a running gait are going to avoid one motor doing work on the other. We end up with this. So that's pretty cool, because I like that it looks like a bird. I just didn't do it on purpose, I promise. It's going to be able to steer, so there's a gimbal up here to allow the legs to do this kind of steering. On the outside of this body is going to be a lot of thick foam, so the robot can fall and not harm itself. And hopefully we'll be able to make it look really cool too through the shape.
So how many degrees of freedom is it?
4 per leg. So 2 degrees of freedom. There's adduction, abduction, and yaw at the gimbal. And then this motor here is leg swing, and this motor here is leg extension through this 4-bar linkage. And here's a spring, and there's a spring. So the same kind of sprung motion. All of this is unsprung mass still. All the motors are still up pretty high. We got a lot. The reason this works for us too is because we're a lot more comfortable now diverging a bit from the ideal spring mass model. ATRIAS was supposed to be the perfect spring mass model. This is not. It's off a little bit, but I think it's definitely close enough to capture what we want to capture. And we've also made our own transmission. So this part right here is electric motor. This part here is transmission. That's a 3 kilogram steel bar on our prototype system bolted to a table. So it's got some, I mean, that's faster than I can move my arm. And it's at 1/7 peak torque right now.
Okay, that was just a huge safety violation.
Should I not show this video? Yeah, we also had him hanging from it and it lifted him up.
That's got sharp edges.
We sanded him off a little bit.
It's kind of
It is made of iron. I mean, it is kind of a hard thing. You wouldn't want to, yeah. Okay, moving on. So how do I take this out of the laboratory and create things? There's a lot of engineering behind it. We want to have actual engineers doing that engineering. The research stays in the laboratory, but development and so on goes to the company. So we've started Agility Robotics. Damien Shelton here, also a RoboGrad, is our CEO. I'm the CTO. If any of you are graduating soon and starting to think about legs are cool and I know dynamics really well and you're looking for an interesting thing to do, we'll have spaces in Corvallis in Oregon and we'll have spaces here in Pittsburgh, I expect and hope. So where do we want to go? This is the big picture view. I want to change the retail economy. Now how do we get there? If you imagine FedEx robots doing the last say a fleet of autonomous cars and then the curb to doorstep delivery, all of a sudden makes delivery costs 10 times less, happen within half an hour. And now, why would you shop? Now there's so much less reason to go to the stores. Everybody in their individual vehicles and taking all of their weekend to go shopping. You just Amazon it and it shows up on your doorstep within half an hour. I think that changes a lot about how many stores do we need, how much energy is used for all of that. How much does it cost really cutting down on market friction, things like that. Now I think there's a lot of steps before we get there. And there's a couple of grand challenges before this is going to work well, like the perception and the sensing and basic manipulation. These are all very hard problems. But the one thing I think that we know how to do is solve the mobility problem and be able to get around with legs as well as a person can get around with legs in the world. What other applications exist? I really think that, again, like smartphone, it's going to evolve in ways that we'll know more in 10 years, we'll know more in 15 years about where this is really going to be useful. But I fully expect that we're going to see legged machines starting to really be part of society and existing, and you're going to see them walking around outside and in factories and doing useful things in the world instead of just being curiosities and shows. That's really what we want to do. Thank you very much for your time. What did you ask me, Howie?
What's the cool video you're going to show in 5 years? Acrobats, college, I think.
That's fine. So in half a year, I hope to have video of this thing kind of running through the forest, like you'd be watching an animal running through the forest. Nobody touching it.
In half a year?
Yeah. Let's see. Yeah. Well, I mean, sometimes the clock is running. Sometimes the clock is running. Are you writing that down?
No, I was going to film you saying that. But I don't think you're going to say it again.
9 months. Soon. We don't have a lot of time.
Howie, you just did film him saying that.
Oh, sure enough. Now we're going to do it in fast order here. We're going to have Cassie built by the end of the summer. We have the same simulation that we validated on ATRIAS with the Cassie model in it. Walking, running, turning, squatting down, standing up, doing a lot of things we want to do right away. I have a lot more confidence that we're going to be able to transition that straight over to the robot. It's a complete physics model of the robot. It's not a reduced order or a simplified model. So I think after we build it this summer, I'm hoping before the end of the year, we'll have it walking around outside. With ATRIAS, right after we had it in the lab, we took it outside and just to see how it would do in grass with the expectations that we were going to have to spend another 5 or 6 months tuning and refining. And it walked just like it did in the lab over the grass, and we were surprised to see it go through a hump in the grass and didn't even notice, and then pavement and back, and then over a manhole cover, and then up a hill and down. So I think we're going to be able to do that with Cassie as well. What we won't do is have any perception on it and be able to, like, we'll trip on a log.
It'll be impressive if you have a remote control driving one of these robots through the forest and around.
Yeah.
That's an amazing capability.
Yeah, and we can buy the first-person view, drone racing goggles, and then drive this thing around. Won't that be fun?
Yeah, play video games.
We'll be there.
Thank you, John.
Thanks. Question?
When you were designing ATRIAS,
Yep.
you said that you wanted it to embody the spring mass model.
Yes.
And so did you ever consider using a parallel elastic topology instead of a series elastic?
Yes. So a parallel elastic topology has that motor gearbox thing that I showed back in one of the slides with a spring in series. And so what that means is when you're standing on it, you don't have to apply any torques with your motor to hold yourself up. You can use a spring. But it also means that when you hit the ground, that inelastic collision exists and is still there. That's one of the big problems. The other thing is that now you are really constraining yourself to one particular configuration and one particular motion. You can't move your leg differently unless you're fighting that spring to get yourself to a new configuration. Those are the reasons we didn't really consider a parallel elastic configuration. But there's also been some studies showing that even for an idealized system, the series elastic can be every bit as efficient as a parallel elastic. I think it was, who's it at Michigan? David Remy, who was looking into that. I don't remember the details, but we did think about that. Anybody else? Garth?
So you showed the Raver somersault video.
Yeah.
You leave us hanging? I'm not gonna.
What's that?
You're gonna try somersault?
No. So that robot is really just an end effector. It has hydraulic cylinders to angle the leg, and it has air cylinders for the leg compression. And then the hoses going off to another room where there's, in that era, a refrigerator-sized computer, but also a multi-kilowatt hydraulic compressor and a multi-kilowatt air compressor to run this thing. So the reason you can do that flip is because it has just raw power being focused through these actuators at the end. I'm much more interested in having something that only takes 100 watts and runs around in the woods.
Well, you also said that you can store energy in altitude and you have a concentrated mass. So it seems like some potential is there for working towards that.
Sure. I mean, it depends too on how big are these, and how much energy can we store in it? Have you seen the videos of people wearing the spring leg, and you can run 40 miles an hour? It's pretty amazing. As if you put some more springs on your body, you can really get some performance, and people are doing big flips and things like that. So if we wanted to optimize for that, we could. I want a 60-pound robot that takes 100 watts that can do everything a person can do and be in human environments and that sort of thing. So I don't think we're going to be doing front flips just because we're not going to try. Yeah?
It's interesting that your new robot is unintended looks like a bird.
Yeah.
Can you share your thoughts on the structure of human leg?
Sure.
Especially having straight during stance and using bipedal.
I think we are a local minima on the genetic optimization. I think we are grounded hairless monkeys. Does that answer your question? So birds come from a long lineage all the way back to dinosaurs. And so if what you're trying to do is run well, maybe birds are a better way. Humans are pretty good. It's hard to judge if they're better or worse. It depends on what you're trying to do. Humans are better at climbing a tree, that's for sure. I don't know. But I have thought about this in terms of why this configuration. This is what happens too if I don't understand feet, and I don't. I don't know how to do a foot yet. With ATRIAS, I think about a spring mass model. It's a point foot. We add this just to prevent the twisting when we go into 3D. That's it. It's completely passive. It's a pin joint at that spot. Now, for Cassie, we're going to try on this first version to have ankle torques so that we have some ideas about how we incorporate that into the spring mass, into our control ideas, how we can apply small torques throughout stance and so on and have that be incorporated with the rest to work. But that's like the simplest step into having a little bit more complexity. So we want to take very gradual steps in that direction. I think that there are going to be strong applications for humanoid-style robots. People are going to want them for one reason or another. Or they may be beneficial because we create our environment to be like us, and we want robots to be able to inhabit that environment and sit in seats and go up and down stairs and things like that. So I think there may be a good reason to build humanoid robots and if you build humanoid robots, you're going to have to understand feet. You're going to have to understand how that damping works at that initial impact to accelerate your fat legs, so you don't have such lightweight legs, all your muscles are on your legs, to accelerate like that, and then how that roll to the toe works and how the push-off works. Why all that happens, I still don't understand. So we're a little ways away from doing a humanoid. Question?
You made comparisons between output force of ATRIAS and humans. How do the physical parameters like stiffness and inertia?
I don't know. I know that with Mabel, the big blue robot, somebody saw the YouTube video and estimated the stiffness that they measured by watching the deflection, and it actually matched pretty close to what people do. I think it's probably in the same vicinity because you see the ground reaction force is the same, and that's all from spring deflection going through the same kind of behavior. You know, another thing I'll mention, that ground reaction behavior, the reason I made the AMASK is a lot of the people in the biomechanics community say, oh, we observe people going from hard surfaces to soft surfaces, and we measure that their leg stiffness changes. What they were doing is measuring leg deflection, and they were measuring ground reaction force. Where I think they made a mistake is saying that those two are directly proportional and calling it a stiffness. They don't know that those are related. They just know for that track of data, there's a certain force trajectory and a certain deflection trajectory. It's a combination of the control that you're putting into your motor and the springs and the damper that creates that particular force. Really can't, it's not even necessarily captured by an impedance unless you say I'm changing my impedance throughout the stride. It can't be captured quite that way. So, I don't know.
Have you considered using this sort of dynamic control model to do things other than walking, like manipulation?
So we did think, because we have some expertise in passive dynamics, and we also have some expertise in how to do force control. We have series elasticity. We can measure the deflection of those springs. We can control our forces very well. I think in Hartmut's lab, you guys have done some of that with ATRIAS, tracking the forces that you're applying. And I think that could be very useful for manipulation. The thing is, one of the reasons all of this stuff is so important for walking and running is because of that dynamical phenomenon that exists. Because of that spring mass kind of oscillation that you want to excite, that you want to generate. And I'm not sure that exists so much for manipulation. So for manipulation, I think that maybe changing your co-contraction to affect the stiffness of your joint and so on is actually important and useful. I think there's so much more, I don't know, all these libraries, motion libraries and things like that, that I think matter a lot more for manipulation. I think it matters to do good force control. I think it matters to pay attention to passive dynamics. You don't want a rigid arm that when you hit something, it breaks it. But there isn't the same cyclic motion that you can generate from manipulation. There was one over here. Okay.
Well, it's just not so much that question, but the previous two. How much do those answers change when you change what's above the hips? So much as you go, let's say, more to a higher center of gravity,
Sure.
potentially a variable center of gravity, would that change the required gait of the robot?
No. So if you have a very high center of mass, now it's just an inverted pendulum that you're balancing. This thing has to be balancing dynamically anyway. You're going to have to, I mean, people do. You have to balance, and that's fine. It's actually, we found with ATRIAS, that center of mass being so close to the hip, the dynamics were so fast, it was actually a problem. We didn't like it. I would choose to put the center of mass farther from the hip right there. I don't know, it doesn't really affect things very much though. So this could be a pelvis and there could be an upper body and manipulators or a sensor mast on the top, or it could come down low and things like that. I think there's a lot of choices. Let's see. Ralph, you had a question?
So back in the day, you were investigating mechanically adjustable compliance. Is that completely dead these days? Or?
There's a thriving community. I believe it's completely unnecessary for legged locomotion. I think that maybe variable compliance is useful for manipulation tasks because of the bandwidth issue. You can't have a perfect actuator unless it's a haptic device. That's a near perfect actuator, but a magnetically levitated haptic device. But if you've got all this inertia and things in your robot arm, this passive dynamics are just going to get in your way, and if you have an impact or things like that, it's going to be a problem. In order to deal with that, you have to create passive dynamics that are going to allow you to have a smaller impact and do better force control. So maybe for that, if you want to do precise position control, like grab a router and just freehand, you want a very stiff joint. If you want to play beer ultimate and run around a field without spilling your beer, you're going to need to relax and have all your stiffness be really low. It would have to be done mechanically if you have realistic high torque actuators. If you have a hydraulic actuator, if you have electric motors that have a reflected inertia, then you have to put something else down the chain in order to make up for that problem. If you have a direct drive or magnetically levitated or magical actuator of some sort, then of course you can do it all in software.
Can you not draw the same analogy to walking also?
Sure.
You were talking about
Yeah.
how if you have to be very precise and careful, you have to be stiffer. But with walking, right? I mean, the same question that I asked before. If you have to step over certain parts of the terrain,
Yeah.
then don't you have to have stiffer legs so that you can do it more precisely?
I think that's a great point. So what I'm thinking about is winter in Pittsburgh, and you step on some ice and then you stiffen everything up, co-contract, and then you think very carefully about where you're placing your feet. It's a good point.
Okay, but you have to keep in mind that you're accurately placing your foot during swing when the leg is unloaded. So you have this limb that's designed to hold your body up and is really beefy to do that. And then you're asking for it to basically do an accurate swing, which is sort of a completely different mechanical regime. And you know, it's very different from your arm, which picks the loads up or applies forces. You know, when we're applying forces, we don't care about positioning accuracy for the leg, and when we care about position accuracy, we're not applying external forces.
I guess the analogy that he just made seems to somewhat contradict that. Right? If you step your feet down and you start slipping, then you have to do both.
Yeah, I mean, you do co-contract, and it is probably useful, but you also often just push your foot down in that situation.
In some fairly blind manner, some kind of flail.
That's right.
So one thing that these robots will never be able to do that a couple of demonstrations from Boston Dynamics were able to do, they have almost magical actuators, these really amazing high-performance hydraulic devices that can apply forces pretty precisely and go fast. When they give a kick to spot and spot, you can see almost the Al Rizzi style sequential composition transition to a new, they decided it's too fast to do the standard walking gait, I'm just going to switch to the highly damped, I'm going to stop gait. It puts its foot out and it just absorbs that energy and stops. You can't do that when you have a giant spring there. The spring's going to compress and now you've got energy and it's going to bounce. But I think that an animal, if you really kicked a dog that hard, first you should be punished, but second, it would bounce and hop a couple times. On its feet, you know. Think like a scientist, people. Think like a scientist.
So, what is your response to Google, who wants to define CMU graduate Astro Teller, wants to turn roboticists to more useful purposes, and doesn't really care about all this stuff?
I didn't understand that question. So what do I think about Boston Dynamics? I have thoughts. Who's Astro Teller?
He's the head of Google X.
Okay.
He's a product of Manuel Veloci's lab. He received a PhD
I know what you're saying.
CMU in 1999 in sort of robotics.
Sure.
Neural nets. And then somehow he was sucked into the dark side of the force. I hope that's on tape.
Yeah. I suspect, I don't actually know anything, but I suspect there's a lot more going on than just, oh, we don't think robotics are a good thing. Because they kept all the other robotics companies that they bought.
No, they repurposed those people. They attached
How do you know that?
They sucked all the robotics out.
Yeah. How do you know that? Is it because of the Bloomberg article where somebody was speculating about something they saw?
Astro said himself, I put the parasites in their ear.
Okay. I mean, I don't know about the internal Google politics. I don't know. But I know that Boston Dynamics has a vision for what they're going to do and how they're going to do it. And if that vision and that goal didn't match with what Google wants, then, you know, things might change. I think that's the politically correct way to summarize my thoughts about this.
One more question.
One more
then we can
question.
let people go.
Okay.
What do you think about the recent developments which are happening in deep learning and walking approaches?
That's a great question. I'm glad you asked that. When I was talking with Gil Pratt about this at the DRC, he was interested in this because he thinks that people are going to make machines move and walk and do all the things using deep learning, and then it's too late. Nobody will ever understand how or why it does what it does because you just hit it with the learning hammer and it worked. I think that all of that stuff is really going to be helpful for fairly noisy and nonlinear and difficult to model systems. So we're starting to think next about how do you do foot placement, how do you do planning through the dynamic space for this weird hybrid system, how do you go up and down stairs. And part of it is, if you think about it, even if it's possible, and it is, to have a great model, think about the dynamics, plan ahead a couple of steps so that you, like a person does, so they're getting ready for the step on the stairs. You probably can't do that in real time easily on a robot right now. Model predictive control with fuzzy it's tough. But we can probably learn some really strong heuristics that are going to recognize a certain scenario and implement a kind of physics-based heuristic very similar to the 6 points I described. I think that's probably similar to what people do. You've evolved or something, some basic heuristic to do that. And I think that some of the machine learning is going to help us solve some of those problems.
I think we're like 10 or 12 minutes over at this point, so I'd like to thank Jonathan for a great talk.
Thank you.